Hello, I'm Chiara Marullo. In this poster, I will describe a work that we are recently doing at ICAR CNR in Naples called Energy Transformer with the Kolmogorov-Arnold module. The impressive performance of transformer model comes from their large number of parameters, which help them to capture complex pattern data. However, this complexity also makes it hard to understand how they work internally. A more explainable and theoretical version of a transformer architecture is the new energy transformer, which uses significantly fewer parameters compared to the classical transformer while maintaining similar performance across different tasks. Inspired by this simple transformer version, we propose a new model that we call Energy Transformer Kolmogorov-Arnold Model, ETCAN, which is a modification that integrates a Kolmogorov-Arnold network in the energy transformer architecture to further reduce the number of parameters. So our model is a combination of different architecture. First of all, it is a transformer. So given an initial set of input token, it will transform the representation into a desired set of output token. Then, as it suggests the name, it is an energy-based model. So it will compute on a set of input token an energy value that describe how good or real looking the connection collection of input token is. The inference process can be seen as a process of taking the input collection of token and repeatedly transforming it by minimizing the energy. This is done by a gradient descent that actually describes a dynamical attractor system that guarantees to converge to a fixed point and serve as a way to perform an error correction of a corrupted data. As I already told you, we incorporate in our architecture a Kolmogorov-Arnold network. This takes inspiration from a Kolmogorov-Arnold representation theorem that informally states that a multivariate function can be decomposed as a sum of simple functions involving univariate transformation. This equation can also be seen as a two-layer neural network, where in the first layer we have n neurons, and in the second layer 2n+1 neurons defined by the capital letter phi. This can be generalized in this way for a network with a fixed number of layers through a composition of different phi functions. Here we can see a sketch of a transformer architecture in the case of three-layer fixed three-layer. Okay, now that we have all the ingredients, we can define our energy transformer Kolmogorov-Arnold block. This is defined through an energy function that is a sum of two different functions applied in parallel, the energy attention and the CAN energy. The first function, so the energy attention, is more or less like the attention mechanism of the classical transformer and is designed to be low when the key token are aligned with the query token. The energy defined by the CAN network instead is defined through a CAN network in order to get an energy that best fits the data provided. The two energies are summed together and then minimized. We applied our model to the image reconstruction task. So we take an image, we divided it into patch, and we masked a percentage of some patch. By applying the energy transformer Kolmogorov-Arnold module recurrently, we have a convergent to a fixed point attractor state corresponding to the completed image in which the missing part of the source image are completed with a plausible representation of them. Here we can see the comparison of the loss between the energy transformer and our model ETCAN. And this is done in the case of 55% of masked patch. As you can see, the two loss almost overlap, confirming that the performance of the two models are indeed comparable. But what we can highlight is that our model architecture allows almost 10% reduction of number of parameters.